Okay, so this is lesson 1.10, exploring types of discontinuities. That's part A, and then we're going to do limit of composite functions. Okay, what are the types of discontinuities over an interval? First, what is a continuous function? A continuous function, loosely explained, is kind of saying that when the curve can be drawn without lifting your pencil. So if you can draw the curve and never lift your pencil, then it is continuous. That is not a rigorous definition, but good enough that it makes sense. So it's going to go forever to the right and then forever to the left. So it is continuous. There's no gaps in the domain here. When is it not continuous? There are 3 types where it's not continuous. And what is not continuous? It is when the curve cannot be drawn without lifting your pencil. Okay, so what are these 3 types of discontinuities? Type 1 is when you have a hole in the domain. So if it goes, this one's going to go forever to the left as it is. Then as we get closer here, we're going to have to lift our pencils and get to the other side and continue on with the domain of the function where it is defined forever. This discontinuity is fixable in order to be defined on the reals. You can just go ahead and define it at that point, and that makes it continuous forever on all reals. So this one is fixable, but it is a discontinuity. Type 2 is when you have a vertical asymptote. A classic example is y equals 1 over x. Again, we cannot plug in 0 for x because we will get 1 over 0, and that is undefined. So it's not defined at x equal to 0. You have a vertical asymptote. So the function is just as we get closer and closer to 0 from the left, the outputs go to negative infinity. They go to negative infinity and never really approach, never get to 0, because it cannot get to 0 because it's not defined. Same on the right, it will go to positive infinity, but it will get close and close to, as we get closer and closer to 0 from the right, it'll go to positive infinity. If we talk about, is it defined or no, is it continuous? Let's say on the interval from -2 to +2. From -2 to +2, it is not continuous because it has a vertical asymptote in between. And that's non-removable. You cannot fix this. It will always be not continuous from -2 to 2 on that interval. This is a jump discontinuity when you have a function that the limit from the left here on this one at 0 is this number here, and the limit from the right getting to 0 is this one here. This is called a jump discontinuity. There's another jump discontinuity here. There's a gap in between there. So we have 2 jump discontinuities here. There's a jump discontinuity here and a jump discontinuity here. And those are not fixable either. Okay, so now for each function, identify the type of discontinuity and where it is located. So we're looking for discontinuities. If we're only just looking for discontinuities, we can just find where is it not defined on the domain. So let's go ahead and factor both the top and the bottom. Top, x, let's see what are the numbers. Is it 2 and 6? Couldn't be 2 and 6. Could it be 2 and 6? Yes, it is 2 and 6. 2 and 6. And they're both negative. Yeah, so those are the factors. This one's going to be x and x. And this one's going to be positive 2, positive 5, positive 5, minus 2. Okay, so what we could do here is cancel out the factor of x minus 2 and x minus 2. And when you cancel out x minus 2 over x minus 2, it creates a hole in the graph. So then it creates an equivalent function here that we can say it is going to be now x minus 6 on top and x plus 5 at the bottom. But we have to remember that x cannot equal 2, because if I plug in 2 in for this here, it'll be 2 minus 2 will create a 0 here, which we cannot have. But we've created a hole there at that point. So when it says find the type of discontinuities, then we can identify each. So it would have a hole here where we cancel it out, and it would create a vertical asymptote at x equals negative 5, because negative 5 plus 5 is 0. So you would have vertical asymptote at x equal to negative 5. So whenever factors cancel out, it creates holes, and when they don't cancel out and the factor is at the bottom of the fraction, for that x value that makes the bottom 0, it would be, that's where the vertical asymptote is at. Let's go to problem number 2. So let's factor the bottom here, x squared. It's a difference of squares here. We can continue factoring the second term, the difference of squares here in the second terms. X plus 2, x plus 1, x minus 2. So x minus 1, I'm sorry, x plus 1, x minus 1. X squared plus 1. The second factor could be factored out. Some more. So this is what we got. We can cancel out x plus 1 on top with the x plus 1 at the bottom, creating a hole. So that's going to be a hole at x equals, let's see, negative 1, meaning that x cannot equal to negative 1 because there's a hole there. There will never be a problem here with the x squared plus 1, because you can input any number here and it will always be positive. So there's no problems here when you have it at the bottom of a fraction. The problem is you don't want to have zeros at the bottom of a fraction, and there's no problem here. In this one, there's a problem because x cannot equal to positive 1. So it has a vertical asymptote. So we'll have vertical asymptote at x equals positive 1. And x cannot equal to 1 because it has a vertical asymptote. So when it says identify the type of discontinuities, it has a hole at x equal to 1 because x cannot equal to negative 1. It has a vertical asymptote at x equal to 1. Next, problem number 3. X plus 2 is already a factor. The bottom we can factor out in x plus 2. Again, cancel out x plus 2 and x plus 2. We have an equivalent f of x 1 over x function. And let's remember x cannot equal 2. X cannot equal to negative 2. And that's where the hole is at. So it has a hole at x equal negative 2 because x cannot equal to negative 2. And it has a vertical asymptote at x equal to 0. Okay, this is removable because you can, holes are removable. This is not removable. Factor out what? 3x here. Then we got 2x plus 3. We can cancel out 3x here. So it's going to be f of x equals 2x plus 3. Cancel 3x with 3x. X cannot equal to 0. So it only has a hole here. So x cannot equal to 0. That one is a hole. So hole at x equal to 0. But there's no problems here because it's just a linear function which is defined everywhere. So it only has a hole here. There's nothing we can do here. One of the things you guys do sometimes is try to cancel this with this, which is absolutely wrong. That is not correct. This is a factor as it is, so we leave it as 4x plus 5. So you would need a 4x plus 5 in order to cancel on top. So there's nothing we can do here. But the bottom cannot equal to 0. Cannot equal to 0. So let's just find out what that x value would be. Cannot equal to 0. The bottom cannot equal to 0. So 4x is equal to negative, cannot equal to negative 5. Negative 5 divided both sides by 4. X cannot equal to negative 5 over 4. And this is going to be a vertical asymptote here. So it has a vertical asymptote at x equals negative 5 over 4 because it cannot, it's not defined there. So this is not removable at x equals negative 5 over 4 because it is a vertical asymptote. Okay, we'll stop there.